welcome back to Math 30-2. We're in Unit 3, Logic and Set Theory, and we're going to be talking about set theory shortly. But before that, I want to go through checkup number 1. If you've not had a chance to do checkup 1, pause the video, do the checkup, and then come back and check your work. So for the first question, you're asked to determine which of the following sentences are statements. And then once you know that, you're asked to classify each statement as true or false. So I'm going to go through and check off the sentences that are statements. B is not a statement because it says basketball is the best team sport. This is a matter of opinion, not something that could be declared as fact. And so C is not a statement. F says this sentence is false. Well, this is an ambiguous case. There's no way to determine if it's true or if it's false. It's just a sentence, so it's not a statement. If we take a look at A, it says Italy is a continent. Italy is actually a country, so this is false. All integers are whole numbers. Well, in order to be a whole number, it has to be 0, 1, 2, and so on. But integers can also include negative numbers, so this is a false statement. B says root 2 is irrational. This is true. And it is not Sunday today. Well, I happen to be recording the video on a Sunday, so this would be false. But depending on what day you watch the video, your answer may have been different. For number 2, we're asked to write the negation of each statement in question 1. And so for A, to negate that statement, we would say Italy is not a continent. And before it was false, now it's true. For B, root 2 is irrational. Root 2 is not irrational. It was a true statement before, and now it's a false statement. For D, it is not Sunday today. The negation of that would be to take the not out. It is Sunday today. And again, for my purposes, it is a true statement now. And then for E, it says all integers are whole numbers. Well, this one can sometimes be a little bit tricky in terms of where you put the not. We want to negate all of the integers, so we would put the not at the beginning. Not all integers are whole numbers. All right, on to number 3. Explain the difference between a conjunction and a disjunction. Well, most importantly is to think about the key words. A conjunction means and a disjunction means or. So for a conjunction, it means that both A and B have to be true. In order to make the whole thing true. And so an example, it says to provide an example, one that I had was it is winter and it is Sunday. Well, it is winter and it is Sunday, so that would be a true statement for me. Italy is a country and baseball is a sport. That would also be a true statement. But if I said it is summer and it is Sunday, one of those statements is false, so then the entire statement would be false. For a disjunction means or. So this is A or B or both. So an example I had, it is winter or it is Sunday. It's true that it's winter. It's true that it's Sunday. It's a true statement. Italy is a country or baseball is a sport. Those are both true statements. It is summer or it is Sunday. Well, it's true that it's Sunday. It's false that it's summer, but it's still a true statement. So hopefully that gives you a few examples. Number 4, you're asked to consider the natural numbers that are less than or equal to 15. So when you're doing questions like this, it's helpful to list your entire set to begin with. So we've got 0, 1, 2, and so on. For numbers that are odd and multiples of 3, we have 3, 9, and 15. X is a factor of 9 or a multiple of 4. Remember, factor means we're breaking it down. Multiply means we're starting at a point and getting bigger. X is even and X is prime. There is only one even prime out there. So that's what this would mean. It's an even prime, and the only option is 2. And then X is a multiple of 2, 3, or 4. So we're listing all the numbers that are multiples of 2, all the numbers that are multiples of 3, and all the multiples that are numbers that are multiples of 4. All right, and then the last question is just so you have an understanding of the difference between inclusive or exclusive. These aren't questions that you'd ever be tested on. It's just so that you're clear on how we're using or in math. And so the first one says to get to the concert, Kiara will drive or get a ride. That means she will drive or get a ride, but not both. This is exclusive. We don't use this one in math. This summer, Trey will play volleyball or travel to Europe. He could play volleyball and travel to Europe, so this is inclusive. So that means he's traveling to Europe, or he's playing volleyball, or he's doing both. This is the one that we use for math. All right, so once you've had a chance to check your checkup, mark your checkup, check off your understanding, and then I'll give you directions in class for what to do with that checkup. All right, so we're going to start talking about set theory. And so a lot of this is going to be formalizing what we talked about in our last lesson. I'm going to give you some more vocabulary to look at, but now we're starting to look more closely at the notation and how we actually denote sets. So first of all, a set is just a collection of objects. So an example here, it says the set of the numbers on a die are 1, 2, 3, 4, 5, and 6. When we're writing out sets, we always use capital letters. So notice the D there, it's a capital letter. And we put our elements inside curly brackets. You could also see the set determined or written this way, D with squigglies like this. Okay. Actually, sorry, not so much that as seeing the elements in the squigglies. So now an element is all the objects or the numbers in a set. And so these are denoted by lowercase letters. All right. So the full set, the set itself, the description, the set D, that's a capital letter. The letters inside of the elements, or the letters inside of the set are the elements, and those are lowercase letters. So for example, the number 5 is an element of the set of numbers on a die. So we say 5 is an element of D. You've seen this symbol before because we've talked in math before when we do domain and range, we say X is the element of reals. So that would mean X is a number that's inside the real number system. The number 7 is not an element of D. So it has 7, but then our element symbol is crossed out. 7 is not an element of D. Now it says, note that every element in a set is unique. The same element cannot be included in a set more than once. So if we had a set, let's say we're doing statistics and we had a set and 5 occurred more than once, we only write the 5 down one time. Now when it comes to representing a set, there's 3 general ways to define the contents of a set. One way is to list the elements of the set. So you'd list the set name and then the elements in squiggly brackets. You can describe the set in words. So 1, 2, 3, 4, 5, 6 would be natural numbers less than 7. Notice it doesn't say less than or equal to. We can also use set builder notation, which you've seen before when we've done domain and range. And so this would be read as X such that X is less than 7 and X is the element of the natural numbers. So just some other things to note. The curly brackets together is read as the set of. This little line here is read as such that. That's why I said X such that X is less than 7. And then the E symbol there is read as is a member of, or I've often heard it as is an element of. Now another one that sometimes can trip people up is N of A. So this means the number of elements in A. So N of D is 6. When you see this N, we're looking for one number. We're looking for the amount of elements in that set. All right, so let's take a look at how this all relates to examples. So up at the top here, the first one says, consider the following two sets. So the first one is whole numbers less than or equal to 3, and then even whole numbers less than 10. So anytime we're working with sets, it's important that we start off by listing our sets so that we can see all the numbers in front of us. So all of the whole numbers less than or equal to 3, remember whole numbers include 0. So 0, 1, 2, 3. And set Q is even whole numbers less than 10. Notice it doesn't say less than or equal to. So 0, 2, 4, 6, and 8. So looking at that information, the first one says N of P. So how many elements are in P? Well, we've got 4 elements in P. And the number of elements in Q is 5. If we wanted to write P using set builder notation, P is the whole numbers less than or equal to 3. So we start off with P. And then we've got P equals X, such that X is less than or equal to 3. So X is less than or equal to 3. Remember, the less than symbol looks like an L tipped on its side. And we also have to note that X is an element of the whole number system. So comma, X is an element of whole numbers. So that would be the full set builder notation. Now, these are often questions that people get a little bit tripped up on, but often, anytime you're doing a test or an exam, you're going to be able to see that notation written somewhere so you can use it as a model. Which of the following is set builder notation that describes set Q? I'll give you a minute to take a look and see which one you think. And the answer is C. So the first one says X such that X is less than 10 and X is an element of whole numbers. This does not indicate even numbers. In order to be even, it has to be multiplied by 2. The next one says that E is equal to 2X, and we go from 0, X is greater than or equal to 0, and X is less than 10. Well, if I were to actually start listing that out, 2 times 0 is 0, 1 times 0 is 2, 1 times 2 is 2, 2 times 2 is 4, and so on, all the way up to 9 times 2 is 18. Well, this is significantly bigger than what we had before. And if we check out on the bottom one, it says 2x, 0, x is greater than or equal to 0 and less than or equal to 5. Well, 2 times 0 is 0, 1 times 2 is 2, all the way up to 5, 5 times 2 is 10. Well, we don't want 10 to be included. If we go back to the middle one where the answer actually is, if I start plugging those in, 2 times 0 is 0, 1 times 2 is 2, all the way up to 4 times 2, which is 8. So sometimes these questions are best done if you actually calculate out the numbers and see which one matches your set. All right, example number 2. So the universal set is defined as all non-negative single-digit numbers. And then from that set, we're going to have other sets that are defined. So E is going to be the set of even numbers, and that will be even numbers that belong to the group of non-negative single-digit numbers. L is whole numbers less than 7, and O is odd numbers less than 7. So we'll start off by filling in all of that information. So we want to list all of the even numbers that are non-negative single digits. Okay, 0 is considered even. Whole numbers less than 7. And odd numbers less than 7. All right, so we're going to be using those numbers on the next page, so you might have to flip back and forth a little bit. Before we go any further with the examples, I want to look at some more vocabulary. So first of all, we've already talked about universal set. The universal set is the set of all of the elements in the group, and we use the symbol U. So you've seen me using that already. Now, subsets are sets that can fit within the bigger set. So it's a set that contains some, all, or none of the elements from a previously defined set. So if we go back to our last screen there, we were given a universal set. E, L, and O are all going to be subsets of the universal set. So it says all sets we work with in a problem must be subsets of the universal set, and every set is a subset of itself. So A is a subset of A, B is a subset of B, and so on. If all of the elements in a set are also in set B, then we can say A is a subset of B. So for example, if I had a universal set of 1, 2, 3, 4, and then one of my subsets was 1, 2, and one of my subsets was 2, I could say that A is a subset of the universal set, B is a subset of the universal set, but I can also say that B is a subset of A because everything in B also is in A. If A is not a subset, then we would denote it as A not a subset of B. So if it is a subset, it looks like a little C on its side or a little U on its side. If it's not a subset, then it's crossed out. If A is a subset of B and B is a subset of U, then we can actually do it almost like a chain reaction. A is a subset of B, B is a subset of U. And if that's the case, then we know that if A fits in B and B fits in U, then A also has to fit in U. Kind of goes back to our number system. We know that all natural numbers are whole numbers. We know that all whole numbers are integers. So then we know that all natural numbers are also integers. All right, and then there's a couple examples further down here I'll give you time to look at as you peruse your notes. I've already given you an example above. Now there are times where we could have an empty set, and that's a set that contains no elements. And if it contains no elements, we denote it using this symbol. And the empty set is a subset of every set. So if we're looking at, I'll actually say that till we have an example later. So here's an example right here. It says given E is 2, 4, 6, the set of all odd numbers in set E is empty because there are no odd numbers. So if I'm given this set, 2, 4, 6, and then I'm asked for the set of all odd numbers in set E, well, the answer would be empty set because there aren't any odd numbers in the set of even numbers. And then the last one is a complement. When we're looking at complements, these would be all of the numbers that are not in the set A. So for example, in our universal set from the last page, we were looking at all of the non-negative single-digit numbers. And then if I looked at my first set being the even numbers, the complement would be all of the odd numbers. All right. The complement of set A can be written as A with a prime symbol, or it can be written as A with a line over top. Okay. Now, if we take all of the elements in the set and all of the elements in the complement, we should have the universal set. All right, so let's go back to our original example that we had on the last page. And the first question asks us to state the universal set as defined above. So before it said all single-digit non-negative numbers. So that would include 0 and so on. Now, we can also list it using words. This would be all non-negative single-digit numbers. Now, if we're looking back at examples of a subset from the sets above, E is a subset of the universal set, and O is a subset of L, which is a subset of U. And so at that point, if you need to, pause the video, take a look back, check them out to see how it is that those are subsets. And then we're looking for an example that is an empty set. And I mentioned this one already before. All odd numbers in set E would be an empty set because there's no odd numbers in that set of even numbers. Now, if we're looking at the complement of set E, just as a refresher, set E as a refresher was 0, 2, 4, 6, 8. So the complement of E would be all of the numbers that are not in E but are in the universal set. So 0 is already in E, 1 is not in E, 2 is in E, 3 is not, 4 is, 5 is not, and so on. So to check to see if you've got them all, we can check between the subset E and the subset not E, and it should combine to be the universal set. 0, 1, 2, 3, 4, and so on. And it does, so we've got the complement. Now for example number 3, we're given more sets here again. And as you're doing this again, it might be helpful to write out all of your sets, which we'll do here shortly. A says the natural numbers less than 20 that are divisible by 3. That means numbers that 3 can divide into evenly. B is natural numbers less than 20 that are divisible by 5. And then C, numbers that are multiples of 6. So first of all, it says, based on the sets provided above, what would be an appropriate universal set? Well, that's kind of guided right here. All of your natural numbers less than 20. So U would be all of your natural numbers less than 20. Now again, you could try writing this out using symbols as well, but in this case, I think words are the most clear. So we'll start by listing all of our sets. A, we're looking for all numbers that are divisible by 3, that are less than 20, so 3, 6, 9, 12, 15, and 18. And then B, we're looking for numbers that are divisible by 5. And A, we're asking for the complement of A. So the complement of A would be everything that's not in A, but is in the universal set. So we've got 1, 2, 4, 5. And again, use your squiggly brackets. Now, if you were to look at B here, B is the natural numbers less than 20 that are divisible by 5. So if we were to make a description of the elements of the complement of the set of B, well, these would be all natural numbers less than 20 that are not divisible by 5. So all natural numbers less than 20 that are not divisible by 5. Now take a moment to look at these last 3 statements and ask yourself whether they're true or false. If you need to pause the video for longer, you can do that. So the first one asks to state whether or not the following is true or false. So the first one is asking, is C included in A? In order to be a subset, okay, so is C a subset of A? In order for C to be a subset of A, every single element in C has to be in A. So C was all of the multiples of 6. So if we look at the multiples of 6, that's less than 20, we've got 6, 12, and 18. And if we look up at A, 6, 12, and 18 are all in there, so this is a true statement. C is a subset of A because everything in C is also in A. Number 2 says C is not a subset of B. Well, if we look, 6, 12, and 18, there's numbers in C that are not in B, so this is true. It's not a subset. Now, the complement of A is included in the complement of C. Well, if we look at the complement of C, this will be a fairly long list. If we look at the complement of C, we're going to have 1, so there's a complement of C. Now, in order for the complement of A to be a subset of C, everything in the complement of A has to be in the complement of C. So 1 is there, 2, and everything in the complement of A is also in the complement of C, so that would be true. Now, if I had flipped that, and I had said, is the complement of C a subset of the complement of A? We would have to say no, because 9 is included in the complement of C, but not in the complement of A. Again, at any time, take a moment to pause the video if you need. All right, so the last piece we're going to look at is and or. And we've talked about this before, but we're going to look at it using set notation. So if we're talking about and, the symbol for and is an intersection. And these would all be included on your formula sheet. So A and B. I remember that one because it kind of looks like a curvy N. Okay, so A and B. So the intersection of set A and B is called A and B, and it's denoted using that symbol I just showed you. It's the set of elements that are the members of both sets. We're going to be getting into Venn diagrams in the next lesson, and so essentially what we're doing is we're looking at where the two sets intersect. That would be an intersection. Union means or, and union is the set of A and B that can be in either A or B or both, and we denote it with the symbol AUB. So U for union. And so this would be, if we were doing Venn diagrams, this would be everything that's in A or everything that's in B or everything that's in both. So essentially it would be that entire set of circles colored in. Now, two sets are said to be disjoint if they have no elements in common. Essentially, if I were to draw Venn diagrams, there'd be no overlap. Okay? So let's take a look at some examples here. So if I was given the sets 0, 2, 4, 6, 8, or my sets E, L, and O, the intersection of E and L would be all of the numbers that are in both E and L. And so that would be 0, 2, 4, 6, 8. And then if I was looking at the union of sets E and L, this would be E or L. So this would be all the numbers that are in either E or L or both. Notice this is a longer list. And then the set of E and set of O are disjoint because they have no elements in common. So essentially it would be an empty set. Now we talked about this before, but A, if I'm looking at all the sets, the elements that are in A and in the complement of A, those combined should give me my universal set. So A union the complement of A is the universal set. And the intersection of A and the complement of A should be the empty set because they should have nothing in common. All right, so let's take a look at a couple more examples here. We're given our sets defined. So the universal set is all natural numbers less than 20. A is all the numbers less than 20 that are divisible by 3. B is all the natural numbers that are divisible by 5. And then C is all the natural numbers that are multiples of 6. So the same sets that we had from before. Again, if it helps, list those down. So for A, we'd have 3, 6, 9, 12, 15, and 18. For B, we would have 5, 10, 15. And for C, we'd have 6, 12, and 18. Again, having those numbers in front is sometimes easier to put it all together. So for the first one, if we're looking at the elements of the following sets, and we want A and B, we want all of the elements that are in both A and B. And if we look, the only one there is 15. If we want to look at A or B, that means it's in A or B or both. So we'd have 3, 5, 6, 9, 10, 12, 15, and 18. Now again, when it comes to the complement, sometimes it's easier to write out your complement. So again, the complement of A So there would be our complement of A. So that comes from our last page as well that we had done. So 1, 2, 4, and so on. And if we look at all of the elements that are in the complement of A and in B, there's a 5 that's an overlap. There's a 10 that's an overlap. And that would be it. So there's a 5 and there's a 10. Now, you might not have had to write out the entire set because B only has those 3 pieces. So you could have said, well, 5 is in B and it's not in A, so that must be in the complement. 10 is in B and it's not in A, so that must be a complement. 15 is in B and it's in A, so that can't be in the intersection. All right, let's take a look at the next piece here. So it says write a set that's equivalent to B and C. Well, if we look at B and C, there are no elements in common, so the intersection between those two would be an empty set. If we want to look at all of the elements that are in A or C, we would have 3, 6, 9, 12, 15, and 18. And if we look at the intersection for A and C, we would have 6, 12, and 18. All right, so just one more example here. If we add another set, and we're going to call this set D, or a subset of the universal set, we want to figure out all of the elements that are in the intersection between A and the union of B or D. So these ones can get a little bit tricky sometimes. Just like order of operations, you want to deal with your brackets first. So for B or D, I'm going to write that off to the side here. For B or D, all of the elements that are in B or D would be 2, 4, 5, 6, and so on. Unions always have the longer lists. And so if we want to look at A and the union of B or D, so the overlap between B or D and A, we would have 6, 12, 15, and 18. Again, we're going to be getting into Venn diagrams tomorrow, and that will be a way that we can visually represent this, because some of you might be having some trouble writing out the sets in this way. But don't worry, we're going to have another way to do it with Venn diagrams. All right, so the next one is A and B or D. So the first thing we have to do is figure out what A and B is. Well, we know from above here that A and B was 15. So A and B is 15. So it's D plus that 15. So we would have 2, 4, and so on. Then we add in the 15, and that would be our entire set. Now the last one's a little bit tricky. It says the complement of A and the complement of B, but then it's the complement of those. So first you want to figure out what the complement of A and the complement of B is, and that would be this. Again, if you need a moment to pause and take a look at why these are the elements, then feel free to do so. But we've got the complement of A and the complement of B gives us that set. So if we wanted the complement of that, then it's just whatever's not in this list of not A and not B that would be in the complement of that. So we would have 3, 5, 6, 9, 10, 12, 15, and 18. All right, so there's quite a few examples that I've given to you. There was a lot of vocabulary again. If you have questions, please, please, please ask. But once you can get that difference between the A, or the and the or, and then we put it together with Venn diagrams in the next class, I think it's all going to come together. So for your homework, I'm going to ask that you guys do a few questions. They look a lot longer than they are, okay? The best advice I can give to you is to write out all of your sets as they're given to you. But this would be what you're asked to do today. So it's numbers 1 and then 4 through 11. I can write it out long here as well. So we'll work on that in class tomorrow. If you have any questions, let me know. And just a reminder that class is going to start at 10:30 tomorrow instead of 10 o'clock, just because I have a meeting in the morning. All right, guys.